What were we doing? Okay, so we had looked at the end of class. We looked at the relationship between, we were talking about the open top box. We had looked at the relationship between the length, or the length of the square cutout, and the resulting length of the box. And we went through this kind of that's not what we looked at. Don't say. That's better. And we worked this through. We looked at changes in x and corresponding changes in length. So we looked at a change at x, and we looked at a change in L, say x1 and L1. And then we looked at, say, change in x2, change in L2. And we decided, was this constant rate of change or not? Was this constant rate of change or not? What's that? It was constant rate of change. How do we know that? So what was one way we could say that? Okay, straight line, that's kind of that's the obvious one. But so mathematically, what do we do?
There's an equal ratio of each change in x to change in L.
Okay, so the ratio of change in L to change in x stayed constant. Constant ratio reasoning about constant rate of change. And what was that ratio? So for a change in x, how much does the length change? So meaning if we increase the side of the square cutout by so much, what happens to then the length of the resulting box?
Decreases.
By how much? It decreases by -2? -2 times as much as whatever the change in x was. So it's to say it decreases by -2 would imply that it goes down 2 inches. But no, it depends. So depending on your change in x, it's -2 times as much as the change in x. So that was our constant multiple reasoning. And therefore, the ratio of the change in L to change in x is -2. And what was a third way that we could reason that this was constant rate of change? What was a third way we could say this is constant rate of change? Nathan?
We have to do the ratio.
Got the ratio. It's constant.
So, okay, so for every change in L, there's a consistent change in x.
Okay, so you're thinking the right rule, but we got to say it better than that. That doesn't communicate what it is. Can you try it again?
For change in x, there's a consistent change in L.
Okay, so for equal changes in x. So if you use the same change in x in different places, at different starting values of x, equal changes in x result in consistent change in L. So every time that we change the side of the square cutout by 1, every single time the length will do what? Every time I increase the side of the square cutout by 1, the length of the box will
Decrease by 2.
decrease by 2, right? Decrease by 2. Every time I increase the side of the square cutout by 2, the length will go down by 4, right? Our constant rate of change is -2. Okay, so let's look at the volume. So I'm going to kind of do the same thing. I'll go as fast as I can. Please state. We look at delta x and resulting delta v. Okay. So we look at same thing. X is going to go from 0 to 0.5. And then I'm going to look at x going from 0.5 to 1. What is delta x in these two cases? 0.5 both times, right? So I'm going to do the second one first. So let's look at it. So here is delta x going from 0 to 0.5. And what happens to the volume when we do that? It increases, right? So we got that delta. We got a delta x there. That's this one right here, a 0.5. And the corresponding delta v of something, right? Then I'm going to do it again. So now I'm starting at 0.5, and I'm going to let the side of the cutout increase by 0.5. I need to get this on toggling with the arrows. Beg them to do that. Okay, there we go. So here, so starting at x equals 0.5, we get a delta x of another 0.5. And I want to start by, I want to find the corresponding change in volume right there, delta v. Okay, so remember we found that v was 11 minus 2x times 8.5 minus 2x. And again, it's not about memorizing that formula, but given a different situation, could you build a formula like that? That's the real thing. It's not about memorizing this. Could you build a formula like that? Okay, so now I've got this delta x of 0.5 right here, and I want the corresponding delta v, so I can take that 0.5, and I can put it in here, and it'll give me the corresponding delta v, right? So yes over there. Yes over here. Yes. Yes. Lots of yeses. Any yeses in the back? I can take this delta x of 0.5, and I can put it in here 0.5, and it'll give me the corresponding delta v. No. No. That doesn't work. Why? What does this formula take? What is x about? Is it about a change in the side length? No, when you put a number in there, if I put 0.5 in there, what does that formula think? 0.5 what? It's a side length. 0.5 is side length, right? It's going to put 0.5 there. It's going to give us the volume of a box that has a side length of 0.5. It doesn't know that we wanted a change, that we put in a change and we want a change. It's just going to do what it does, which is you put a number in, it's going to interpret that number as a side length of the square cutout, and it's going to spit out corresponding volume. All right, so then if that doesn't work, how are we going to get the change in volume? I want to get this change in volume right here. When x changes from 0.5 to 1. So, we need to know how to do this. How am I going to get the change in volume? Is it John?
Yeah.
Tell me. When are you going to get that change in volume? Not sure. Michael?
You would still be doing a final minus submission for it, wouldn't you?
Okay, yeah, so now we're going to need a final volume minus initial volume. So, Allah, how am I going to get the final volume?
I think it's gonna be 3.7 something if we look into the y-axis.
That would just be, okay, but that would just be estimating. So I want to get this exactly. How can I get the final volume exactly?
Then it's gonna be 0 minus initial minus final minus initial, which is gonna be.
So yeah, I'm just at, so I just want the final volume. How will I get the final volume only? Exactly. How can I get the exact value of the final volume?
We'll look at the y-axis, right?
That's an approximation. That's an approximation.
Plug in the x.
Okay, so
0.5.
okay, which x? So what am I going to do?
Plug in 0.5 once and times 0, then minus 10, subtraction.
So if I want the final volume, what am I going to plug in?
0.5 for the first one.
No, we're working on this one. I'm working on, I want this right here. 1. Okay, so to get the final volume, I'm going to take the final value of x and plug it in here to get v. And then I'm going to get the initial volume by plugging in the initial value of x.
And subtract from 0.
Okay, so does everyone see that? So let's write those down here. What is V1? Let's call it V1 for the volume when it's 1. And what is V 0.5? What is V1? Nine times 6.5. And do it faster than your calculator. 9 is 54 plus 5.5. 59.5? Oh, I almost got it. All right, so 58.5. V of 0.5? So 37.5? I think I know that from earlier. Is that right? I'm just going from my memory. What is it? Well, looking at the graph, 58.5 sure seems right. 58.5 sure seems about what we're getting at. That arrow is showing me the current value of V. Okay, what was my other one? 37.5. Remember correctly? Okay, change in volume. 21. Okay, so from 37.5 up to 58.5 is a change in volume of 21. And then we said what? Equal changes in x result in consistent changes in v, right? So this is the same, this is equal change in x, 0.5, so the change in volume is 21 here, right? Because equal changes in x mean consistent changes in v. 21. Yes? Cameron, what do you think?
No, because like the first interval would change at different rates in the second.
Okay, so that, what I said was equal changes in x mean consistent changes in v. When is that true? Okay? Constant rate of linear, constant rate of change, right? Constant rate of change. And what's happening here? It's not linear. It's not constant rate of change. So that's off the table because we don't have constant rate of change. We can't apply these three rules that we've been working on now that, and we're blue in the face, right? So how am I going to get that change in V? I want to get this change in V. Same thing. What is, when the side cutout side length is 0? By the way, can the cutout side length be 0? Is that valid? Lots of you are saying yeah. All right, let's see if I can do it. Ready? Here we go. Ready? I think I can do it. I did it. I've never gotten applause before. Well, that's the first class. I got applause. Right, so it's possible to cut out squares of side length 0. It's just a sheet of paper. You don't do anything. And then you fold up the flaps, and there's your box. You don't have flaps, right? You don't get flaps. Okay, so is x equals 0 a valid value of x?
Yes.
Is x equals negative 0.5 a valid value of x? No, I can't cut negative squares. That doesn't make sense. But 0 makes sense. It doesn't. It feels uncomfortable because you don't get a real box. But mathematically, it's fine. X equals 0. There it is. X equals 0. So what is v of 0? What's the volume? 0. It has no height, so there's no volume. What's the change in volume for this change in x of 0.5 then? 37.5. Okay? So, non-constant rate of change. Equal changes in x give a different change in v. And first, when you increase the side length, how does the volume increase? Moderately, slowly, fast? What's happening? For a small change in x, how does the volume increase? Pretty fast, right? But then as the side length gets bigger, if you increase the side length by the same amount, you don't get that same jump in volume. You get a smaller jump in volume. So the rate is slowing down, right? The rate is decreasing. Okay, I want you to do this one more time for practice. Go from 2 to 2.5. Go. X goes from 2 to 2.5. Delta x is what?
5.
Find delta v. Go. I'll start thinking in attendance. So we may lose this for a second. You're going from 2, x equals 2, to x equals 2.5. Yep. How'd that go? What'd you get? Did you get it? Okay, what are you going to do? So we're going to go from 2 to 2.5. What are you going to do? How are we going to get the change in volume as x changes from 2 to 2.5? Do you follow how we did these? So the change in a quantity. So what's our formula for calculating the change in a quantity? So if my daughter is 2.6 feet, and then a little bit later she's 2.9 feet, how do I calculate the change in her height? What do I do? What is it, sir? I'm not looking for the answer. I'm looking for this question here. If the initial height is 2.6 feet and then final height is 2.9 feet, how do you calculate a change? Final minus initial. You're going to take 2.9 minus 2.6. So same thing here. We need final minus initial. So how do we get the final value of the volume? Cecilia.
So you would find the volume of 2.5 and the volume of 2.
Okay.
And so you would plug this into the volume formula that we have, which is the 1 minus 2x and 8.5 minus 2x.
Okay.
And I got a negative number, so I took the volume.
And what'd you get?
Negative 10.5.
Negative 10.5. Is it right?
Yes.
Negative?
So
Negative volume? You can have negative volume?
So is it possible?
So it's impossible. Impossible?
Negative change.
It's a change, right? Change. So what does it mean? Negative change is okay. Because it means getting smaller. So, right. So if there was, if we were holding on to hope that equal changes in x and consistent change in y, our hopes were dashed here. Well, now they're gone, right? Now it's not even increasing anymore. Now you increase the size of the cutout and the volume gets smaller. So it's the farthest thing from constant rate of change. And let's see that in action here. Here's 2. There's what's happening at 2. You've got for that, you get this volume, something over 60. Increase the square cutout to 2.5, and the volume goes down. We get these big squares. If you make them bigger, then the box gets like taller and skinnier, and you lose volume. Okay. So, just comparing, right? So with the length, if you look at the length quantity versus the side of the cutout, you get constant rate of change. Every time you increase the length of the cutout, the length of your box goes down twice as much as how much you increase the cutout length. If you look at volume, totally different animal, right? The rate that the volume is changing is changing. So the rate at which the volume changes changes itself. It's not constant. The volume shoots up quickly as you increase the square cutout, then it kind of slows down and you get a greatest volume. And then after that, you keep making the squares bigger and your volume shrinks. Gets smaller. Non-constant rate of change. Questions? All right, so let's talk about, so we're talking, all semester we're talking about relationships between quantities, input, and we can think of this kind of like input and output. It's like we choose how we cut the squares, and then something, other quantity results from that. This is this idea of input and output. Okay, so this brings up the topic of functions. So the open top box problem is a context for input-output relationships. Input-output relationships. So as for example, the input is the length of the square cutout, and the output is the volume. So you pick a square, like I just said, you pick a square side that you're going to cut, and that will result in some volume of an open top box. Okay, but not all input-output relationships are what we call functions. Only some input-output relationships are functions. And functions is the land that we live in calculus. Okay, that's where calculus. That's where we do calculus, in the land of functions. Okay, so we've got to know what's special about these particular relationships of two quantities that makes them a function. So let's talk about that. What makes an input-output relationship a function? So a great way to think about this as your phone, okay? Your smartphone. What's the input? So in terms of using it as a phone, okay? Using it as a phone. I know that's like the least thing to use it for now, right? But what is the input when you're using it as a phone? Phone number, right? Phone number. So and your phone book has dozens and dozens of phone numbers, right? And so the input is a phone number, and so then we hit send or whatever, and what's the output? Okay, it makes a call, but what's the output of a particular phone number? We hope not, right? Usually voicemail, right? Okay, but we hope not. What do we hope for? Someone picking up, a person or a place, right? A person or a place. So, for instance, your mom, friend, pizza, customer service, brother, your ex. Okay. So all right. So, how does it work? How does it function properly? When you call a number, you always get this recipient. When you call that number, you always get the right person or place. That's a functioning phone. Okay, so now I'm going to call this number. I better always get my friend. Oh, hey, get ready. So this is a functioning phone, right? And this is the idea of a function. For each input, you get a particular output, and you get that same output every time. Every time you get that same output when you call the same set of numbers. That's a functioning phone, right? It's performing its function. Okay, but what if this? You dial this number, sometimes you get your mom. Sometimes you get the pizza place. All right? Call this number. Sometimes you get your brother. Sometimes you get your ex. So apply your little joke now. Okay. How about this phone? What are you going to do with this phone? Throw it away. What are you going to do? You're going to get a new phone. Why? It's not performing its function. It's not working right. The same input is doing what? Giving different outputs. It's unreliable. It's giving different outputs for the same input. Okay, but what about this situation? Here's another situation. Your friend has two numbers. So when you call that first number, it gets you your friend. And then a different number also connects you to your friend. Maybe he has a smartphone and a landline. Okay? And we know that these big companies, customer service, there's many different numbers to get to the same kind of call center. How about your phone now? Can it keep it? Does it work okay? It's fine. Are we still meeting this criteria? For every number that you call, are we meeting this criteria or not?
Yeah.
Given a number, do we always get the same recipient every time? This number. So am I getting one recipient or more than one recipient? One, my friend, every time. This one, every time I call this one. I'm getting this visa. Okay, I call this one. Every time I call this one, I get. It's fine, right? So here we have more than one input is giving us the same output, but that's fine. That's not violating this. What does this say? Every time you have an input, you pick that input. Every time you pick that input, you get consistent output. It doesn't matter if more than one input gives you the same output. That's okay. That's not violating that rule. So yes. Every input results in one output. The phone is working fine. It's just some places have more than one number that will reach them. Okay, another example. So you and your friend, you go to the lake several times in the summer, and you take data regarding temperature, frogs, and crickets. At the end of the summer, you organize your data into some graphs here. And so you counted rivets, and you noted the temperature several times. And you counted the chirps, and you noted the temperature several times. So the first one, when you counted 2 rivets, you had one particular time, and that was 78. But there were 2 times that you counted 3 rivets, and here were the temperatures of those 2 times. And then 3 different occasions, you counted 4 rivets, and those were the temperatures. Similarly with 5. Function? Is that a function? For a particular input, do you always get a consistent, reliable output?
No.
No. Okay? Now the crickets. So you counted chirps per minute. And you took note of the temperature when you did that. Function? Yes. Okay, so this is getting at what's the deal with this rule, this criteria? You've heard it before in previous classes. For every input, there's only at most one output. What is that about? Why is that important? This is showing why that's important. Who are you going to listen to if you want to know the temperature? Obviously. Are you going to count rivets to know the temperature? No, it's not a reliable mechanism to count or to predict the temperature. But cricket seems to be. It seems this is kind of a true phenomenon in nature. This is true. That there's this deal with listening to how many chirps in a minute predicts what the temperature is outside. Yeah.
Question. So, like, imagine like a square root graph, except flipped on its side. That wouldn't be a function, right?
That's the vertical line test.
Yeah. So. Yeah. Wow. The vertical line test is a really unfortunate kind of thing because it's like this thing we just fall back on, and we don't have to know anything except just saying the words vertical line test, right? So, but your question is what? This is kind of off topic, but you're saying you take this and you flip it on the side?
No, like a completed square root
Like a
graph.
parabola?
Parabola, yeah.
Yes, so sideways parabola. Okay, so instead of just saying no, it doesn't pass the vertical line test, let's apply the rule. So what is it about? So input is
1.
so you pick an input, say you pick an input of 1. So does it pass this? Does for every time you put 1 in, do you get the same consistent output? No, because you could get this output, you could also get this output. Okay, so who are you going to listen to predict the temperature? Crickets. Okay, so this relationship of number of chirps and temperature is something useful. It's helpful in the real world. Okay, one unique output for each input means that a function performs something. It does something with purpose and meaning. Counting rivets doesn't have any meaning for determining temperature. So what do we care about? We care about the relationships that are reliable and functional. like the temperature and number of chirps. Gives us something reliable and useful. That's why we care about this criterion of functions. Okay, so let's go back to our, so what about the volume situation? If the input was square cutout side length, I'll just write X, and the output is the volume of the resulting box in cubic inches. Is volume, is this a function? The input is X in inches and the volume V. Yes or no? Discuss. Is it a valid function?
Yes.
Lots of yes. But we just looked at the graph, right? Didn't we just look at the graph? And we found that. Could I just erase this vertical line test from your mind? Look, you can get the same output more than once, so it's not a function, right? So here at 1, so 60, say 60 cubic inches. Oh, my pen doesn't work. Oh, that worked. Yes? No, I'm on the wrong page. Where was I? Here? It works on this page. Oh, try again. Sorry. Maybe it's this one. There we go. Okay, so here's 60 cubic inches. Well, there's some input here that gets us, but then there's a bigger square that also gets us the same output of 60 cubic inches. So it's not a function, right? Jenna?
That is incorrect. Basically, the spirit of the vertical line test is that for any given value of x, there is only one corresponding value, which y.
Mm-hmm.
And that is true for this graph.
Okay, it's true for this graph. Talk to me in terms of the box and the quantities. How about in terms of the box and the quantities? Can you reason in terms of the box and the quantities? Same thing. Carlo?
It's just a different shape, but it's the same volume.
Different shape, but it's the same volume. But we're saying, is it a function or not?
Oh,
Is it a function or not?
yes.
Why?
Because each foot, it has its own unique output.
Okay, so in terms of the quantities, we'll come back to this.
In terms of the box, for any given cutout side length, you will get one volume.
What do you think about that? Agree with that? You want to add to that?
It's kind of like what you said with the phone thing.
Okay.
You can have more than one number called the same
Uh-huh.
person, so that's kind of like what this graph is showing.
Right. You can have more than one square cutout get the same volume. That's not what a function's about. That's what she said. She said, if you choose a square cutout length and cut that out and make that box, could you get more than one volume? Or you can only get one volume?
Just one.
You'll always just get one volume. Okay, right? So I'm going to choose what? 1.75. 1.75. And I'm going to do this with 1,000 different papers. And I'm always going to choose a side cutout of 1.75 inches. Will my volume of my box be the same for all 1,000 pieces of paper? For all 1,000 boxes? Same volume. Okay? Reliable. So yes, different cutouts can get the same volume. That's not violating the idea that each input only gives you a single output. In this case, each side length cutout gives a particular volume. Okay, so let's talk about domain. So the domain is the set of all possible inputs in a function. So what is our input? We said x. X was our input into this function whose output was volume. And so what are all possible values of x? What are all possible values of x here? So I'll just show you what that looks like changing the square cutout length. And let you talk while I finish attendance, okay? I'm going to finish attendance. What are all possible sizes of squares that we can... Okay, so you can't have negatives. So you're saying, can it be 0? Okay, so am I right in saying that you're saying it's x greater than or equal to 0? Any positive value. Any 0 or any positive value. What do you think? Nick, you agree with that?
No, it can be that, and it can go up to half the smallest side.
Half the smallest, so up until half the smallest side. So you're looking at this and you're saying, oh, there's an upper limit on this. How big can we cut squares? What are the biggest squares we could possibly cut? 4.25. What about squares that are 4.25? So we can end up having 4.25 size squares, right? Is it possible to do that?
Right.
No, listen to my question. Is it possible to have 4.25 squares to cut it in such a way to have that?
Yes.
Yes. Right? So let me just draw the original paper here. Here's the original paper. Sorry, missed there. But there's one. So that's 4.25. That's 4.25. Laugh at me. Fix it. Ha. Okay. All right. So this is 4.25 by 4.25. Same with this one. Same with this one. Same with this one. It is physically possible to do it. It's uncomfortable though, right? Because it doesn't give, like the 0 case, it just ends up being a flat sheet of paper that you fold in two. And what volume do you get? 0. You just get this flat piece of paper sticking out. No volume. Is it physically possible to make x equal to 4.25, though? Yes, you can do it. Can you make x equal to 4.3? Can you get 4 squares that are 4.3 on a side? That you can't do, so that's impossible. So our domain is, we can write it this way, or we can use the brackets, because it means you include the endpoints. So you do this way, x is greater than or equal to 0 and also less than or equal to 4.25, or this notation means the same thing. Square brackets means include those endpoints, parentheses means don't include. So in this case, we want to include. So that's our domain. All values of x or all values of the input that are possible, that make sense. Okay, let's see. Where are we at? Main. Okay. So another way to view functions is like a machine. Okay, so another perspective on functions is like a machine. You're going to put something in this case, length of side of cutout. The machine's going to do something. It's going to take that input and by some process deliver an output. In this case, it's a formula that gives us volume from side length. So in general, input, there's 3 parts to a function. Input goes in, output comes out, and there's a rule that tells us how to get the output from the input. So sometimes the rule is a formula, like in the volume formula, but not always, okay? Like your input could be age, and output could be your height. So the rule is just, at a particular time, at a particular age, you're so old, you have a particular height. And so the rule is kind of implied, but not necessarily a formula. Okay? Or the rule could be given by a table or given by a graph. Okay, so here's symbolically how function notation works. We know V is our output. Okay, so here's the deal. F is the name of the function. F is not a variable. It's a label. Okay, it's not a variable. We don't say that F is changing. F is a name that just means the whole relationship. So it's not synonymous with V. V and just F are not the same thing. Okay, so V is just a label. It represents the relationship itself. Okay, and then there's input. Our input is X, and we see that here in the formula. And then that's the rule. So you have input, output, the name, and the rule. But the thing we want to work on now, which is really important, is looking at, say, this whole thing right here. Look at that. So if I were to give you a choice, is that the input, the output, the name, or the rule? What I put a box around. Is that input, output, the name, or the rule? What do you think?
Input.
That's input. What I put a box around is input. Agree with that? Jay, what do you think? You think it's the input? Agrees. What's that? Input, output, name, or rule?
Output.
Okay, well look, it equals V. Do you see this? What I put a box around equals V. So what does it have to be?
Output.
Output. So for instance, f of 2. When you see f of 2, this may conjure up the thought of, I'm supposed to do something. F of 2. Oh, I'm supposed to take 2, and I'm supposed to do some kind of process, do some kind of arithmetic, and get an answer. Okay? But that's not the way. I want to change your thinking about that. F of 2 is an output. So we can use f of 2 in any setting to represent an output of f. What particular output is it? F of 2 is the output of f. But which output is it? What's that?
When the input is 2.
When the input is 2. That's the way you want to think about it. F of 2 is the value of a quantity. It's the value of the output when the input is 2. Rather than seeing that as, oh, that's telling me to do something. That's telling me to plug and chug. Jacob.
I know you said that f isn't a variable, but could you look at f of x as a whole as a variable?
It's a value of output. It's not. Yeah. So yeah, because it's v. So
Like, in a sense, but not. It's not a variable like, that you can define.
Yeah, by variable we usually mean something like v or x. So this is an expression that has the same meaning as the output. Yeah. So it's an expression. So it's not a variable. It's an expression. Okay. All right. So we need to practice this. So what? You're going to talk to the person next to you. That's probably even further away, so I'll do it here. Okay, so I want you to practice. What are the meanings of these expressions? Okay? Can you read that? Sorry. It's a lot easier on my computer. One more time. Okay, so we got 4 expressions there. So, grab your calculator, right? No, that's the point. I'm asking you for the meanings of these. I'm not asking you to crank out something, okay? I want to know, if you just see that as part of a bigger expression, what would the meanings of each of these be? So talk it out. Take turns, okay? Go, talk it out. What do these mean? Okay, what are they? Talk about them. Okay, so I'm hearing lots of you say the word plug. You're missing the point. It's not about plugging something. It's not about doing something. None of these things are about doing something. They have a meaning. They are a value. They are some kind of value. You're describing the meaning of the value. It's not a command to do something. You gotta change your thinking on that. Okay, so how about f of a? Jake, what's f of a?
I think that it's the same as like f of 2, the original.
Well, forget about that. I want to hear what f of a is. Tell me what f of a is.
Well, when the output of f of a is the output of f when the input is a.
It's the output of f when the input is a. It's an output quantity. So it's a volume. It's a certain volume when the square cutout length is a. Okay, f of 3 plus h. Tell me your name again in the blue shirt.
Austin?
Austin, tell me about f of 3 plus h. What does that mean?
F of 3 plus h is the output of f when the input is 3 plus h.
The output of f when the input is 3 plus h. Right, and is that, what kind of thing is that in this case for our function? What kind of quantity is that? What kind of number is that?
Not sure.
What kind of number is that? Is it a temperature? Zach, what is it?
Is it gonna be like
What's that? Is it a volume?
Yes.
Yeah, the output of the function f is always volume. It's volume. For this particular f, right? So defining this volume function, right? So that's going to be a volume. Okay, what about f of 3 plus h? How about that one? Jonathan.
It's the output of the input of 3 h added to it.
Okay, so it's the output of the function f when the input is 3, and that output with h added to it. So it's h more than the output of f when the input is 3. So you see the difference between that. So you see the difference between 2 and 3. 2 says you're going to input 3 plus h and get a particular output. 3 says you're going to input 3, you're going to get the output for an input of 3, and then add h. Okay, what about 4? Tell me, I forget your name. Tell me.
John?
John, how about 4?
Well, it's, in my mind, it was kind of like the final minus initial thing, but it's that output of f of 4 and then minus the output of f of 1.
That's true, but I like where you were starting with. So what the whole thing, what does it mean?
Like, it's the final minus initial kind of thing.
What do you get when you finalize initial? What is that?
Your current volume, or the volume you're looking for.
No.
Oh, the change, sorry.
So what change? The change of what? It's a change of what quantity?
The volume, I guess it would be in this case.
Change of volume. And what particular change of volume is it? What's that?
The change of the output of f when the input is 4 to when the input is 1.
So talk about the box. So it's the change in volume when what?
The side one.
Side lengths change from
4 to 1.
4 to 1?
1 to 4.
1 to 4? So is this starting or final value of x? That's the starting value of x, and that's the final value of x. So as this is the, someone had their hand up, they're dying to say.
No, I was just gonna say the side length of the cutout, not the side length.
Right, so tell me the whole thing. What does the whole thing mean?
It's the change in volume.
Change in volume.
The change in the side length from 1 to 4.
Right, it's the change in volume.
Change the side length of the cutout.
It's the change in volume. If you were to increase the side of the cutout, start with 1 and increase it to 4. You get that would calculate then the change in volume. Do you see it? So this is kind of so we can use function notation then to represent like a delta v, right? See, that's a delta v, and that's a particular delta v, starting at side length 1 to side length 4. Okay, next page. So just some semantics here. If we say p is a function of s, then p is the output and s is the input. Okay, so by saying p is a function of s, we're saying p depends on s, right? P depends on s. So p would be the output depending on s, the input. If you say p in terms of s, again, that means that p is the output and s is the input. So when we get into these application problems, and they set up the problem and they use one of these, they use this language, what I find is students get confused and they say they dive into the problem, but they never knew which quantity was input and which was output, and so they're confused from the beginning. So when you see these phrases, either p is a function of s, p in terms of s, p with respect to s, we've got to identify what is input and what is output. So p with respect to s, again, is saying that p is the output and s is the input. So it's like p equals g. That is p with respect to s. P is the output, s is the input. Or p in terms of s. S squared plus square root of s minus 1 over s. That's p in terms of s. S is the input, p is the output. Okay, does it mean that when you have a phrase, the output always comes first and the input always comes second? No, you can write it. There's a dozen ways you can set it up. You have to read the particular situation and determine which quantity is output, which one is input. All right, so flip to page 84 in your workbook. You got your workbook? I know we haven't used it much in class, but keep bringing it. We're going to use it, okay? So flip to page 84. All right, so they say following table shows the average monthly rainfall, and this is number 4, given the number of months since January 1st. All right, here's the deal. Consider average monthly rainfall with respect to the number of months. Average monthly rainfall with respect to the number of months. What's the input and what's the output? What is the input quantity? You want months? Okay, it wants months. Agree with that? And the output is? Amount of rainfall. Valid function or not? Talk to the person next to you. Is that a valid function? If the input is how many months and the output is the amount of rainfall. Valid function or not? Yes or no? Okay, what's your name? I forgot. Yeah. Valerie, what do you think? Valid function or not?
I think it is valid function
Because?
because it has, for every input has one output.
Every input has one output. That's right. Every input has one output. You pick a certain month, since January 1st, there's only one amount of rainfall in that month. Okay? Valid function. Okay, what about if we turn the tables and say we want the number of months with respect to the average monthly rainfall? Number of months with respect to average monthly rainfall. Why not a function?
Because now the input is the same.
Right? Well, putting the same input in many times that's okay,
We gotta have a different output.
but then you get a different output. So if we put 1.1 inches in, that points to different numbers of months. It could be after month 1 or month 2 if you have 1.1 inches. So as soon as you have something like that, it violates the function. Okay, flip over to 88. So let's bring graphs into this. Is this on page 88? This is what I want. I want you to work A through E. A through E on page 88. Is that number 4 on the page? Yeah, number 4, A through E. If you can't see a book, then share with somebody so you can both see it. Is everyone able to see a book? Glad you're thinking about it. Most students just look at the numbers in the graph and they don't. That's good. Maybe it's not realistic, yeah.
I feel like it could be, but it's just like, yeah.
So are you working on it? So for B, change the order, right? Do this first. Answer this first. And then do this second. That's the way we want to think about it. There we go. Again, on E, do this first. So what does it mean first? And then if you get to it, then evaluate it. But that's the important question. So f of 60, hopefully we're there by now. F of 60 is what? What is f of 60? Dan,
It's how much he weighs 60th day.
how much he weighs on the 60th day? It's the output when the input is 60. The output when the input is 60. That's right, how much he weighs on the 60th day. Okay, so then what is f of 200 minus f of 160? Freddie, what is f of 200 minus f of 160? What's that mean?
The average change of the weight of between the weight. It's the weight of it on the and the day 160 and the 200 the change the weight.
It's the change in weight.
Yeah.
Okay, so it's the change in weight. It's a good start. So let's finish that off. So which change in weight is it? Freddie, keep going. Which change in weight is it?
Change in weight in sound of
Any change in weight? It's a very particular change in weight. We know exactly when that change in weight occurred. When did it change? From when to when?
from 160 days to 200
Right. From 160 days
to 200.
to 200 days. It's a very it's a specific change in weight. Is that what you guys were going to say? So it's the change in weight, 160 days to 200 days. Okay, flip back a page. I want you to do number 2, A through D. Read carefully. A through D only. Okay, show me your answer to A. Show me your answer to A. Make sure you got A ready. Okay? So it's not an equals. It's not something equals something. It's just, boom, it's just the answer. How do you express, what are they asking for? Populations. How do you express that population? It's not something equals something. It's just one expression. Yeah, so we don't want to write equals. So what is it? So how do you express that population? Right. So yeah, so this is okay. We're just using function notation, basically function notation. So we'll see. Becca, did you get the first one? What'd you say? H of k. For that first one, h of k. That's exactly what that function does. K years after 1990, h of k tells you what the population is, k years after 1990. All right, what's the meaning of h of k plus 3? Zach?
It's just adding 3 more years after 1990.
Okay, but you didn't tell me what h of k plus 3 is. What is h of k plus 3?
It's the population.
Population.
After 1990, like 1993.
So this is the population in 1993? So how many years after 1990?
Like given amount of years plus 3.
Yeah, so it's not 1993 that this is the population of. It's k plus 3 years after 1990. Or what were you going to say, Jacob?
I said it's a given amount of years plus 3 after 1990.
Okay, and so what does the whole thing mean?
The
Population.
of Blacksburg.
Okay. Yeah, population of Blacksburg. The easiest thing to say would just be k plus 3 years after 1990. Or you could say k years after what? This is the population of Blacksburg k years after when? 1993. You're adding the 3, so that starts you in 1993, and then k years after that. So you could say the population of Blacksburg k years after 1993 would work too. All right, so a population that's 765 more than the population in the year 1996. Let's see. Kate.
Would be h of 6 close parentheses plus 765.
This is what she wants. What do you think? That's right. Okay, last one. The change in population from m years after 1990 to m plus 7 years after 1990. Tell me your name again.
Nick.
Nick. Did you get it? The change in population starting at m years after 1990 to m plus 7 years after 1990.
Just do h parentheses n plus 7.
So you say h of m plus 7
Equal. Oh, I didn't get
So we want the change
change.
from m years after to m plus 7 years after.
Oh, minus h.
That's the thing you need to know how to do. That's really important. So that's a change in population starting m years after 1990 and ending m plus 7 years after 1990. So in the next hour or two, I'm going to add some more to your wet work. And then I'll post the written. It'll all be finalized by 5. And I'll see you Tuesday. Have a good weekend.